everyone, and welcome to another deep dive. Today we're going to explore the hidden physics in the stuff we see and use every day.
Yeah, physics can seem like it's all about complicated equations and stuff that's way out there.
Right.
But the truth is, it's about the laws that govern everything around us, like from the smallest atom to the largest galaxy.
Exactly. And to help us uncover these everyday mysteries, I've got a fellow physics enthusiast here with me, ready to break it all down.
Absolutely. And we're going to take a look at some fun examples from like a physics lesson between a dad and his daughter.
Nice.
And some insights from this Italian physics text I was reading.
Cool.
It's going to be pretty amazing.
I'm ready. Let's start with something that seems pretty basic. Density.
Okay.
You know how much stuff is packed into a given space?
Right.
In our source, the daughter's asked about the density of water, and she says 1.
Ah, yeah, that's a classic misconception. A lot of people think water is just water.
Right.
But it actually has a specific density like anything else.
So density is all about the relationship between mass and volume.
Exactly. It tells us how much matter is squeezed into a space.
Okay, to make that a bit more concrete, let's say we've got a 1-liter bottle of water.
Okay.
We all know it holds a specific amount of water.
Right.
But the density tells us how much mass is packed into that volume.
Exactly. And a 1-liter bottle of water weighs about 1 kilogram, which means the density of water is 1,000 kilograms per cubic meter.
Whoa, 1,000 kilograms per cubic meter. That's a lot denser than I would have thought.
Yeah, it puts things into perspective, right?
It does.
And you know what's even cooler is comparing the density of water to other materials.
Oh yeah, like what?
Like rocks, they've got a relative density of about 4 or 5.
Okay.
And then iron comes in at about 7.8.
Oh,
Mercury's even denser at 13.5.
wow.
And then you've got gold at a whopping 19.
Okay, gold's heavy.
Yeah, and then we've got uranium at about 20.
Okay.
And at the other end of the spectrum, you've got these super cool things called aerogels.
Aerogels, I've heard of those.
Yeah.
They're like basically weightless, right?
They're solids, but they're so light, they're almost as light as air.
Mind-blowing.
Yeah, it's like they challenge our whole idea of what a solid can be.
That's so cool.
Okay.
Okay, so now that we've got density down, let's talk about something that might surprise you. The speed of water coming out of your kitchen faucet.
Okay.
I bet it's faster than you think.
Yeah, maybe.
So picture this. You're timing how long it takes to fill that 1-liter bottle from your faucet.
Okay.
Let's say it takes about 7 seconds.
All right.
Now, how do we figure out how fast the water is actually moving?
Well, we need a bit of physics, but it's not too complicated.
Okay.
The formula is V equals Q divided by S.
Okay, break that down for me.
So V is the speed we're trying to find.
Okay.
Q is the flow rate, so how much water's flowing out every second.
Got it.
And S is the cross-sectional area of the faucet opening, basically the size of the hole.
Makes sense.
So we need to figure out how much water comes out every second and how big the opening is. And we already know that 1 liter of water came out in 7 seconds.
Yeah.
So our flow rate, or Q, is about 0.14 liters per second.
All right.
Now, to make the calculations work, we got to convert that to cubic meters per second, which gives us 14 times 10 to the minus 5 cubic meters per second.
Wow, those are some small numbers.
Yeah, they are.
Right.
Now, for the faucet opening, let's just say it's about 0.6 centimeters. We need to convert that to meters, too.
Right, and don't forget about pi.
Oh, yeah. We need pi for the area of that circular opening.
Good point.
So we plug all those values into our formula, and what do we get?
Drum roll, please.
The speed of the water coming out of your faucet is about 5 meters per second.
5 meters per second. It's like 17 kilometers per hour.
Exactly.
That's way faster than I imagined.
Yeah, it's pretty surprising, right?
Yeah.
A gentle stream of water moving that fast.
It's crazy to think about.
It is, and it actually affects all sorts of things, like how plumbing systems are designed and even how water erosion shapes landscapes.
Wow, I never would have thought about that.
Yeah, physics is everywhere.
Now, no deep dive would be complete without talking about air.
Right.
And get this, we can actually measure the speed of air being blown through a straw.
Now that sounds interesting.
It uses something called a venturimeter.
Okay.
And we can make one using just 2 straws.
2 straws. How does that work?
So you take 1 straw and cut it in half.
Okay.
Then you put that cut straw in a glass of water, so it's partially submerged.
All right.
And then you take the other straw and hold it just above the opening of the submerged one.
Okay, I'm picturing it. So we blow air through 1 straw, and it affects the water level in the other one.
Exactly. When you blow through the top straw, the fast-moving air creates a low-pressure zone near the opening of the submerged straw.
Okay.
And that causes the water level in the submerged straw to rise.
So the faster the air moves, the higher the water level rises.
Precisely. In our source, blowing through the straw caused the water level to rise about 5 centimeters.
5 centimeters.
Yeah.
Okay.
And here's where it gets really cool. We can use Bernoulli's equation to figure out the speed of the air.
Bernoulli's equation, I vaguely remember that from physics class.
Yeah, it's a key principle in fluid dynamics.
Mm-hmm.
Basically, it says that as the speed of a fluid increases, its pressure decreases.
So the faster the air moves, the lower the pressure it puts on the water in the straw, causing it to rise.
You got it.
Yeah.
We can use the numbers from our experiment, like the density of water gravity and the height the water rose, and then solve Bernoulli's equation for the speed of the air.
And what does it turn out to be?
About 1 meter per second.
1 meter per second. That's about 3.6 kilometers per hour.
Right, so even blowing air through a straw has a measurable speed, and we can figure it out using physics.
Isn't that neat?
It's incredible. It's amazing how these simple concepts are all around us.
It really is. And the more we look, the more connections we find.
Absolutely. Okay, so we've talked about the density of water and the speed of air, and we even touched on Bernoulli's equation.
Yeah, we did.
But we're just getting started. Next, we're going to dive into the world of ice.
Ice. All right.
And uncover the physics behind its strange behavior.
I'm intrigued.
Like, why does ice float?
Yeah, that's a good question.
And we'll explore the molecular structure of water and its weird connection to the world of comic books.
Comic books. Now that's something I gotta see.
It's going to be good. Stick around. All right, so you're back and ready to dive into the chilly world of ice.
Ice. Yeah, it's something we see all the time, but it acts pretty strange.
Yeah, like why does ice float? It seems like solids should sink in their liquid forms.
Right. Well, it all comes down to the way water molecules arrange themselves when they freeze.
Okay, so there's something special about the structure of ice.
Exactly. When water freezes, its molecules form a crystal structure with a lot of empty space.
So it's not just that ice is lighter than water, there's more to it.
Right. It's about how those molecules are arranged. One of the sources used this cool analogy called the Mickey Mouse model.
The Mickey Mouse model, I like where this is going.
Yeah, so picture a water molecule like Mickey Mouse's head.
Okay.
The oxygen atom is Mickey's face, and the 2 hydrogen atoms are his ears.
I can see it.
And this bent shape is really important for how water molecules interact.
Okay, so how does that shape lead to ice floating?
Well, when water freezes, these Mickey Mouse-shaped molecules link up.
Oh.
And they form this lattice with these gaps in between.
So it's like a 3D network with holes in it.
Exactly, and that makes ice less dense than liquid water, where the molecules are all jumbled up and closer together.
So those tiny Mickey Mouse ears are the reason ice floats?
In a way, yeah. The source also mentioned another way to visualize it, called the Mercedes-Benz model.
Mercedes-Benz, interesting.
Yeah, each water molecule is like the 3-pointed Mercedes star.
Okay.
And just like with Mickey Mouse, these stars arrange themselves in ice with spaces between them.
So whether it's Mickey Mouse or Mercedes-Benz, the message is the same. Those gaps make ice less dense.
Exactly. Now, you know what would be a cool way to think about this on a bigger scale? Remember that Uncle Scrooge comic where his money bin freezes?
Oh, yeah. Paperino e la ghiacciata di dollar. Classic.
Right. In the comic, his money bin freezes solid and it causes all sorts of chaos.
That's a lot of frozen money.
It is. The comic says the money bin is 3 acres cubic.
3 acres cubic.
Which is kind of weird because an acre is an area, not a volume.
Right.
But let's assume each side of the bin is 1 acre, which is about 4,000 square meters.
So it's a huge money bin.
Yeah, a side length of about 60 meters, which seems about right from the drawings.
Okay.
Now, with the side length of 60 meters, the volume is 216,000 cubic meters.
That's massive.
It is. So how much water would it take to fill that bin, assuming it was full of water and coins?
That's a good question.
Well, we need to think about how densely packed the coins are. The source mentioned an experiment where they packed a bunch of 10-cent coins, and they got a density of about 0.55.
Okay, so we're using real data to figure out this comic book scenario.
Yeah. Now, a dollar coin is about 1.1 cubic centimeters.
Okay.
But factoring in the packing density, each dollar coin takes up about 2 cubic centimeters.
Okay.
So if we divide the total volume of the bin by the volume per coin, we get an estimate of $100 billion.
$100 billion. Scrooge McDuck is loaded.
He is. But here's the crazy part. The amount of water needed to fill that bin would be 90 million kilograms.
90 million kilograms. That's like a whole lake.
It is. And to freeze that much water, you'd need to remove a huge amount of heat.
How much are we talking?
Assuming it starts at 10 degrees Celsius, The heat removed to freeze it to 0 degrees would be 3.4 times 10 to the 13 joules.
Wow, that's a mind-boggling amount of energy.
It is. It's like enough to power a small city for a while.
So freezing Scrooge's money bin is no small feat.
Definitely not. But you know what we haven't considered?
What's that?
Our calculations assume perfect heat transfer.
Ah, right. In reality, it doesn't happen that quickly.
Exactly. The time it takes for something to freeze depends on how well it's in contact with its surroundings.
So a small ice cube melts faster than a big block of ice.
Right, because the small cube has more surface area relative to its volume.
It's like trying to cool down a hot pan by just touching it with a cold spoon.
Yeah, exactly. This actually reminds me of something Lord Kelvin tried to do.
Lord Kelvin, wasn't he a famous physicist?
He was, and he tried to figure out the age of the Earth based on how fast it was cooling down.
Interesting.
But his calculations didn't account for radioactive decay inside the Earth, which keeps it warmer than it would be otherwise.
So he underestimated the Earth's age.
Yeah, he did. It just goes to show that you gotta consider all the factors when you're applying physics to real-world problems.
Absolutely.
Oh.
Okay, so back to Scrooge's frozen fortune. There's one more thing we should talk about. Salt and ice.
Salt and ice. What about it?
It seems counterintuitive, but adding salt to ice actually makes it melt faster.
Right, you'd think salt would make ice colder, but it lowers the freezing point.
So the ice melts even though it's below 0 degrees Celsius.
Exactly. That's why we use salt on icy roads. It makes the ice melt at lower temperatures.
Makes sense. Okay, so for our last icy mystery, let's go to the bottom of the ocean.
The bottom of the ocean sounds chilly.
What do you think the temperature is down there?
I don't know, probably close to freezing.
You'd think so, right?
Yeah.
But because of water's weird properties and the salt in the ocean, the temperature at the bottom is actually around 3 degrees Celsius.
3 degrees Celsius. That's warmer than I expected.
Yeah, it's another example of how physics and chemistry work together to shape our world even in the deepest parts of the ocean.
It's amazing.
All right, so we're back and ready to explore another cool set of physics concepts: surface tension and capillary action.
These are really interesting phenomena that explain how liquids behave, especially water.
Yeah, surface tension always seemed kind of mysterious to me. It's like water has this invisible skin that lets it do all these crazy things.
Yeah, it's a great way to think about it. Imagine surface tension as this force that makes the surface of a liquid act like a stretched elastic sheet.
Like a trampoline.
Exactly. The surface is taut and resists being pushed in.
So it's like those water molecules on the surface are all holding hands, creating this barrier.
Basically, it's all about the forces between water molecules. They're attracted to each other, and that attraction's even stronger at the surface where they're only touching air on one side.
That makes sense. And that explains why water droplets form those perfect little spheres, right?
Yeah, a sphere is the shape with the least amount of surface area for a given volume.
So the water's trying to minimize its surface area.
Exactly. And that's why droplets are round. It's like nature's way of being efficient.
I love it. Our sources describe some fun experiments that show surface tension in action.
Oh yeah, like what?
Like floating a paperclip or even a needle on water.
Yeah, that one's always cool. You have to be really careful, but if you do it right, the object just sits there on top of the water.
Even though it's denser than water.
Right. You're taking advantage of that invisible skin created by surface tension.
The source said you can coat the object with a little bit of oil or paraffin to make it easier.
Yeah, that's because those substances are hydrophobic. They repel water.
So it's like creating a tiny raft for the object to float on.
Exactly. Another cool experiment is the one with the coin and the water droplets.
Oh yeah, that's a good one. You keep adding drops of water to the top of a coin.
Right. And you'd be surprised how many you can add before the water spills over.
It's like building a tiny water tower.
As the water droplet grows, the surface tension acts like a barrier, holding it in place.
It's pretty amazing. You can even try to inflate the droplet by carefully adding more water or tiny coins to the top.
And eventually the surface tension can't hold it anymore and the water spills over.
It's a great way to see how strong that surface tension really is. Okay, so we've talked about how surface tension lets bugs walk on water and lets us build tiny water towers. But there's also something called capillary action, which is kind of related to surface tension.
Yeah, capillary action is all about how liquids flow in narrow spaces, even against gravity.
Like water climbing up a straw.
Exactly. Or how a sponge soaks up water. It's like the liquid is defying gravity.
It is in a way.
Yeah.
And it's driven by these two forces, cohesion and adhesion.
Right. Cohesion is the attraction between like molecules, like water molecules sticking to each other.
And adhesion is the attraction between unlike molecules.
Like water molecules sticking to the walls of a straw.
Okay, so in a straw, the water is attracted to the walls of the straw, and that pulls it upwards.
Exactly. The adhesive forces are strong enough to overcome gravity, and the narrower the straw, the higher the water climbs.
That's so cool. And this explains how trees transport water, right?
Absolutely. Capillary action plays a big role in how water gets from the roots of a tree up to the leaves.
So it's like a team effort. Surface tension and capillary action are working together to help trees survive.
It's a beautiful example of physics in nature. One of the sources described this really cool experiment to show the combined effects of surface tension and air pressure.
Oh yeah, the one with the jar and the cloth.
Yeah, you cover a jar with a piece of cloth, secure it with a rubber band, and then flip the jar over without spilling the water.
Sounds impossible.
But it works. It's like a magic trick, but it's all physics.
So the cloth has tiny spaces between the fibers, right?
Right. And when you flip the jar, the water starts to push down on the cloth.
Okay.
But surface tension across those tiny gaps creates a seal.
So it's like the water is holding onto the cloth.
Exactly. At the same time, air pressure is pushing up on the cloth from below.
Right, because we live at the bottom of an ocean of air.
So you've got surface tension holding the water up from the top and air pressure pushing up from the bottom.
It's like they're working together to keep the water in the jar.
Exactly. And it's strong enough to overcome gravity even when the jar is upside down.
That's amazing.
Yeah.
The air around us is more than just empty space. It's actually exerting pressure on everything.
Yeah, and that pressure can really affect how liquids behave.
The source also talked about an experiment using a capillary tube to measure surface tension.
Oh yeah, a capillary tube is just a really narrow tube, usually made of glass.
Okay.
And when you dip it into a liquid, the liquid rises inside the tube, even above the level of the liquid in the container.
So it's defying gravity again.
Right. It's called capillary rise, and it happens because of those same forces we've been talking about: cohesion, adhesion, and surface tension.
And the narrower the tube, the higher the liquid rises.
Exactly. And if you measure the height of that liquid column and know the diameter of the tube, you can actually calculate the surface tension.
So we can use a simple tube to measure these invisible forces.
Pretty cool, huh? And capillary action is super important. It's how plants absorb water, how ink flows in pens, even how some medical devices work.
So from bugs walking on water, to trees getting a drink, to water droplets forming perfect spheres, surface tension and capillary action are everywhere.
It's amazing how physics explains these everyday things.
It really is.
Oh.
Well, that wraps up our deep dive into the amazing physics of everyday things.
Yeah, we've covered a lot of ground today.
We have. We talked about density, the speed of water and air, Bernoulli's equation, the strange behavior of ice, and even surface tension and capillary action.
And it's all stuff that we encounter every day, but maybe never really stop to think about.
Exactly. And that's the beauty of physics. It's all around us waiting to be discovered.
So keep exploring the world with curious minds.
And until next time, keep asking those why questions. And remember, physics is more than just equations. It's the story of how our universe works.
Absolutely.